Okay, so the second talk of this section is given by David Saulpic. Please.
Hello, this is yes. So I'm going to present another paper with Vincent, also Andreas Feldmann from Charles University. It's a near-time approximation scheme for some clustering problems in doubling metrics. So as Kartik said, the goal of clustering is to partition data according to similarity. And the data is a set of points in a metric space. So that's the general purpose of clustering. And in this talk, we're going to focus on fixed dimension for some definition of dimension. But some examples of low-dimensional input are image segmentation, facility location, or redistricting to tackle gerrymandering. That's a big issue. Okay, and the model for clustering we use, the function we try to optimize as Kartik is K clustering, so you have a set of clients in some metric space, a parameter T, and the goal is to output a set of facility that is part of the metric space. So K centers of facility that minimizes that objective function. And K median is when T equals 1, K means is when T equals 2. So that's the general model of clustering. So we're going to focus on doubling metrics, meaning metrics with bounded doubling dimension. And the doubling dimension of a metric space is captures its growth. It's the smallest integer D, such that any ball of radius 2r can be colored by 2 to the d balls of radius r. So for instance, in R2, with L2 norm, you can cover the ball of the unit ball by 7 balls of radius half. So the doubling dimension of this is 3. This doubling dimension is a generalization of Euclidean dimension. If you take R to the D with any LP norm, it has doubling dimension theta of D. But we remove some geometric property of Euclidean spaces. So one interest of studying doubling metrics is to see what makes algorithm works in the plane in Euclidean space, to see because they usually work better in that case. And so for clustering problem, we're going to show that this doubling property is great. However, I'm going, for simplicity, to focus on Euclidean plane. Everything works the same, but it's easier to draw pictures. Okay, brief history. So Kartik did a bit of it. In general metrics, you can approximate K-median up to 2.67, K-means up to 9. And it's NP hard to get good approximation for K-median and for K-means. So as it presented at the end, even in Euclidean metrics. But this talk focuses on the upper bound part. So since it's hard in high dimension to get good approximation, we focus on low dimensional spaces. And for K-median, it has been known for 20 years how to get a p-TAS from Koliopoulos and Rao. And this complexity is what we target. We want, or nearly what we target. We want to separate the dependency between epsilon and the dimension D from the dependency in N. So that's our ideal goal. We want something that hides some huge exponential in epsilon and D and a polynomial in N. And we say that is fast. So that exists for K-median, or nearly exists for K-median in the plane. But for K-means, the best known is still super exponential in epsilon and D. That's a work from Vincent 2 years ago. And everything works in Euclidean space. So what we do is we improve the results and make them work in doubling metrics. So I'm going to try to present a framework for designing efficient approximation schemes for a bunch of clustering problems that run in that complexity, which is said fast. Okay. And in the talk, I'm going to focus on back-criteria k-means. So I'm going to allow the algorithm to return slightly too many centers. I'd be happy with 1 plus epsilon k centers if the objective function is less than the optimal with k centers. And in the paper, we show how to remove this epsilon fraction to many centers, but it's getting technical. Okay. So what's the standard? I'm going first to show the standard approach for k-median, and try to explain you briefly why it doesn't work for k-means, and then we show how we modify it to make it work. So we start by building a randomized decomposition, recursive decomposition, called the quad tree. So we simply split the input into 4 boxes and do that recursively. Okay. And we say that the first level of the recursion, the lines we draw to divide the input has length, say 1, and second level they have length half, etc. Then we place some portals on the boundary. For k-median, we need, say, log n portals. And we force every path that crosses the boundary to go through a portal. So that incurs some detour. The detour, if the length of the line is L and we place P portals, the detour is L divided by P. So we want a big P to have a small detour. Yes, and we focus on structured solution, meaning solution where every path from a client, the point, to a facility, the square, has to go through portal every time it crosses a line. Okay, and there is a standard algorithm to find such the optimal structural solution in that complexity. Okay, so that's the standard approach for many problems. However, it doesn't work when you square the distances. If we look at that input, so the points are again client, square, or facilities, the total cost is order n. But as soon as you draw the first line of the decomposition, you're going to separate one client from its facility. So the detour incurred by going through a portal at that level is going to be n, the length of the line, divided by p. And if we square that for k-means, this is bigger than n, except if you take many, many portals. So this approach, this example shows that this standard way of dividing the input doesn't work for k-means. Okay, and that's the main question: how to deal with those squared distances. Okay, so we propose a simple modification of the standard algorithm. We define something we call badly cut for the clients, and we just remove the badly cut clients. Intuitively, these are the clients that are close to a boundary of a high level of the decomposition. And just doing this allows us to place a constant number of portals and make things work for k-means, and everything goes faster because you have fewer portals. Okay, so that's our algorithm. The plan for the talk, so I'm going to define badly cut and try to show how it's useful, how we can use it, and why it is useful. So that's the key notion I want to try to convey. Okay, any question so far? So let's define badly cut. So we start with a constant factor approximation A that we can compute easily. And we define AC to be the distance from a client C to this approximate solution A. Then for any client C, we draw the ball of radius AC over epsilon. And we look at the lines that, in the decomposition, the lines that cut this ball. And we say that C is badly cut if there is such a line larger than AC over epsilon square. So if there's a kind of big line that cuts the ball close to C. Okay, so briefly, why AC over epsilon square? Because if you put, so if all those lines are smaller than AC over epsilon square. And you put a constant number of portals, so epsilon to the minus 2.5. Then the detour to cross the line AC over epsilon square is going to be length of the line divided by p, and that gives epsilon times AC square. And this is a small detour. We're happy with that error. We can charge that error to say that we have a near optimal solution. So when I say small detour, I will mean that quantity. Okay, so that is for Balikat client. We have the same definition for, or nearly the same for Balikat facilities. So instead we look at a facility, its closest facility in the optimal solution, the ball of radius distance between the two facilities divided by epsilon. And if it contains a line too big, then we say that the facility is Balikat. Okay, so how can this be used? The first thing we can see by it's a standard analysis in the quad tree dissection. Any client or facility is Balikat with tiny probability. So the probability comes from the decomposition. The decomposition itself is randomized. So most of the clients are not Balikat. Most of the facility are not Balikat neither. And we can show that if a client and its facility in A are not Balikat, then a constant number of portals is fine. We have a small detour in the decomposition. Okay, so the proof is easy. We look at one client C, its facility F, the green ball of radius AC over epsilon square, and two cases can happen. Either the closest facility in opt is inside that ball or not. So if it's inside that ball, we know that C is not Balikat. So the red line between C and its closest facility in opt must be short. And if the line is short, as I showed briefly, constant number of portals is enough to have a small detour. So in that case, we're happy. Now, if the closest facility to C in opt is not in the ball, it means that it's super far away from C and from F. So we can reassign C to the closest facility to F in opt. That's only a tiny modification of the solution. And since F is not Balikat itself, there are only short lines between F and its closest facility in opt. So there's also a small detour here, and we are also happy. Okay, so if no one is Balikat, everything works fine. We're happy. And most of the people are not Balikat. Okay, so now how to deal with Balikat clients. Okay, any question on that part? Yeah. Okay, so I said earlier that we just remove the Balikat client. That's a bit too rough. So instead of removing it, we said if a client is Balikat, we move it to its closest facility in A. That gives a new instance I prime. Before solving everything, we do that. And then we just focus on the instance I prime. We place a constant number of portals, and we find the optimal structured solution in I prime. So now we have two claims. The first one is that the cost in the original instance I of any solution is close to the cost in I prime of that solution. This is an expectation just because a client is Balikat with probability epsilon. So we move it in I prime with tiny probability, and we move it with a cost proportional to what it pays in the approximate solution. So the claim one is just, okay, we move every client with a tiny probability. Now the second claim is that it's enough to focus on I prime. Finding a structural solution in I prime gives a good approximation of the optimal solution. So that's enough to conclude because we know that cost in I prime and in I are the same, and we know that in I prime we can find quickly an optimal structural solution. So we're happy as well. Okay, so how to show the second claim? My goal is going to show that there are no more Balikat clients in that instance, because we saw earlier that if no one is Balikat, then we're happy. For that, I'm going to consider the solution S, consisting of the optimal facilities plus the Badlicat centers of the approximation, the approximate solution A. So this has slightly too many centers, but since every center of A is Badlicat of probability epsilon, in expectation there is only 1 plus epsilon k centers in that solution. So if a client is not Badlicat, then we are happy. We can serve it with a small detour in the original instance. And if a client is Badlicat originally, so in I prime, we moved it to the facility, to its closest facility in A, and two things can happen. Either the facility is Badlicat, so we had in the solution S, it's opened, so the client is served, that was 0, so everything is fine, there's no detour. Otherwise, the facility is not Badlicat, so the client is not Badlicat neither. So using the former lemma, we can serve it with a constant number of portals. So that's all. That's the proof. So that shows how to, hopefully shows how to use this notion of Badlicat and how to make it work for clustering. Okay, so brief summary of the results we have in the paper. We have that complexity approximation scheme, so efficient approximation scheme for k-means, k-median. So for that, we need to remove those epsilon k too many facilities coming from the Badlicat centers of A. We need to do something more tricky, consider another solution S. It works as well for non-uniform facility location. It gives a few bi-criteria results. And Vincent showed that it can give as well some approximation scheme for capacitated version of the problems. Okay, so now some open questions. This framework make the Aurora dissection, Aurora square tree work with squared distances. So can we use it for other squared distances problem? For instance, to compute the boot mean square matching in the plane, or it's also called the 2-Wasserstein distance. Can we use it to get non-bi-criteria pitas for the outlier version of the problems, or for other bunch of clustering problems as well? Okay, thank you for your attention. And I just want to add that the carbon footprint of this article is more than what a French person should produce a year in order to respect Paris Agreement. Thank you.
So, do you have questions?
What's the difference on K that we got the first time?
No, there's not for any K. And the complexity doesn't depend on K neither.
Other questions? We have time. Okay, so thanks again.